So is it recording now?
Yes.
Yes, thank you.
Good. Good. So let's try to compute scattering time. So let's start with a simple limit of Boltzmann gas. So assume that temperature is much larger than Fermi energy. So the electrons are essentially non-degenerate, absolutely classical particles. We should not worry about Fermi statistics. So in this case, a typical rate of electron phonon scattering is just sum of all outgoing states, wk to k prime. So W is scattering probability. So essentially is the picture is like that. I'm taking an electron with in the state k, its energy Ek, and since temperature is much greater than epsilon Fermi, I should not worry about Pauli blocking. So for me, it's essentially one electron problem. So there is one single electron that interacts with phonons, and I'm computing the scattering probability from state k to k prime. And I'm using a Fermi golden rule for emission and absorption amplitude processes, which is 2 pi. Okay, I apologize, I don't remember whether it's H or H bar. K to K prime square and Q plus 1/2 plus minus 1/2 times delta function that takes care of the momentum conservation. Okay, so let us assume that there are single parabolic band in the problem, single band effective mass approximation. So energy of electrons is essentially k square over 2m with some effective mass. Okay, so now we need to decide what is the so we are computing 1 over tau k, and we need to decide what is the k that we're interested in. Let's assume that k that we're interested in will be thermal k, so epsilon k is of the order of temperature. So thermal electrons, just to make things easier. Okay, so 1 over tau k from expression above is the rate of scattering with absorption of phonon and the rate with scattering with emission of phonons. And the rate for scattering with phonon absorption is sum with respect to k prime and q, 2 pi over h matrix element for the scattering process minus nq, k to k prime square nq times delta function epsilon k minus epsilon k prime plus h bar omega q. And now let me substitute there the matrix element m for the model of deformation potential we discussed last time. So this will be a d-dimensional integral over k prime over 2 pi in the power d. d-dimensional integral over q over 2 pi in the power d. Delta function, now the matrix element m. Let me write the matrix element m. So it will be proportional to the delta function of the momentum conservation, b of q, and then the remaining part of this expression, n, and the delta function that corresponds to energy conservation. Okay, I'm getting rid of one of the delta functions, namely of the momentum delta function, d over k prime, b of q, n of q, delta function of epsilon k minus energy, sorry, q minus k plus h bar omega q. Okay. So let us consider a three-dimensional case, and let us write integral in polar coordinates. So it will be 2 pi over h integral from 0 to kd by dq times q square, integral from 0 to pi sine theta d theta, divided by 2 pi, and this guy divided by 2 pi. Integral over d phi divided by 2 pi from 0 to 2 pi. And then b of q, n of q, and delta function k square over 2m minus k minus q square over 2m plus sq. Okay, now I can write this thing as 2 pi over h, 1 over 2 pi square, because this guy cancels, integral from 0 to kd by, that's the maximal bosonic momentum, dq times q square. And now I can write and call cosine theta, I can call x, therefore dx is sine theta d theta with a minus sign. So I'm having here an integral from 0 to 1 dx bq n of omega q times delta function of k q over m times x minus q square over 2m plus sq. Now I'm performing the integral with respect to x, and I'm getting sorry, no, I'm writing it, just rewriting as 1 over 2 pi h integral from 0 to kd by dq times q, integral from 0 to 1 dx bq n of omega q times delta function k over m x minus q over m plus s. I'm taking 1q. I'm taking what I did. I took 1q from this delta function outside, and therefore instead of q square I have q in the power 1. Okay, now I'm performing integral with respect to x, so I'm getting m over 2 pi hk, integral from 0 to k d by dq times q, b of q, n of omega q. Okay, so this was the story for, and this was, I remind you, was 1 over tau k absorption. So if I add now 1 over tau emission, so 1 over tau k, which is equal to 1 over tau absorption k plus 1 over tau emission k, I'm getting the expression changes into m over 2 pi hk, integral from 0 to k d by dq times q times b of q, and here will be 2n omega q plus 1. So absorption requires a pre-existing photon, emission does not require pre-existing photon, therefore it comes with n plus 1. All other coefficients are exactly the same. So now let us set h to 1, and recalling that in the deformation potential model, b of q is proportional to q, where coefficient of proportionality b0 can be expressed in terms of material parameters. So the density of matter, sound velocity, and electron phonon deformation potential constant. Okay, but so that's not really important for us. These are known constants. We plug them in and we get 1 over tau k is equal to m over 2 pi k b0, integral from 0 to k d by dq times q square 2n omega q plus 1. Okay, this is equal to m over 2 pi k b0. Let us now choose a dimensionless variables. So let's define a variable x equal to sq. So it's not a dimensionless variable. Oh, it is, sorry, s times q divided by temperature. It is dimensionless variable, but I need to divide by temperature. And then it's an integral from 0 to s k d by divided by temperature dx x square 2n of x plus 1 times t over s in the power 3. Okay, so I got 1 over tau k is equal to m over 2 pi k b0 t over s cube, integral from 0 to s k d by divided by temperature dx times x square 2nx plus 1. Okay, now let's analyze different limits of this integral. Limit number 1, temperature much larger than omega d by, which is equal to sk d by, of course. In this case, the upper limit of this integral is much smaller than 1. in this case, SKD by over temperature is much smaller than 1, which means that X will be much, much smaller than 1, which means that both the Einstein distribution function n of X, which is in general equal to E1 over exponent X minus 1, can be approximated by 1 over X. And therefore, so these are large high temperature limit. This is high temperature limit. Temperature is larger than epsilon Fermi. Temperature is larger than omega dB. Temperature is the highest parameter. And so in this case, we get 1 over tau k is equal to mb0 over 2 pi k t over s in the power 3 integral from 0 to s k dB over temperature dx times x, and we are computing this integral, and we are getting that this is equal to mb0 t cube over 2 pi s cube k s k dB over temperature square times 1/2. This is equal to mb0 over 4 pi s k dB square times temperature over k, and this is equal to 1 over 4 pi square k dB cube divided by 2 rho s square m times temperature divided by k dB. Now let me call this thing. This thing has a dimension of 1 over time. So let me define the time scale which appears in this problem. Let me call it deformation acoustic. So this is a nominal time scale for electron phonon scattering. Now, and the remaining guy, am times t divided by k dB, it has dimensions of mv square times m k square. So this has the dimensions of m square v square over k square, and this is just 1. So therefore this guy is dimensionless, as it should. And therefore what we found is that 1 over tau k in this model is equal to 1 over tau bar dA m t k times k dB. So almost all microscopics of the problem, all microscopic parameters of the problem are combined into a combination that we call tau dA. And it may be that our calculations were simplistic or the model was simplistic. Nevertheless, there is one parameter which quantifies the strength of electron-phonon interaction, and it's directly measurable in the experiment. And then the theoretical prediction is that the scattering time at high temperatures is proportional to temperature. So what it simply means that you increase the temperature, you increase the number of phonons. Number of phonons is proportional to temperature. So typically, the scattering in this range, typical number of phonons at thermal Qs will be 1 over epsilon S typical Q divided by temperature minus 1. Typical Q will be K. So this will be typically E in the power SK over temperature minus 1. And then we expand and get that this is, sorry, too fast. Too fast. Minus 1. We expand it and get it 1 plus SK over temperature minus 1. So this is T over SK. And this thing is much larger than 1. So in this scattering process, typical number of phonons is much larger than 1. Typical change of electron momentum is of the order of electron momentum. And the number of phonons is just proportional to temperature. So effectively, phonons act as impurities, but by changing the temperature, you control the number of these impurities. Okay, so that's what happens in the classical limit where there's a non-degenerate Boltzmann gas. So now let us consider situation when temperature is much smaller than Fermi energy. Then we are in the Fermi gas. So what happens in the Fermi gas? Computations are essentially similar, but we need to remember about Pauli exclusion principle. And when we compute 1 over tau k, will be again sum over k prime, wk to k prime. But we need to remember that these are fermions, and the state k prime must be empty. And this is an incoming process. And in this case, the state must be filled. So in the limit f of k prime much smaller than 1, we would go back to Boltzmann gas. And we are using the same value of the matrix element for emission and absorption. Okay, so now we need to repeat the same computation, but taking into account Pauli blocking. Any questions so far? Okay, if everything is clear, so let us now compute these integrals, but let me use a trick, and this is a good trick, and it relies, it uses a very nice idea called detailed balance, and I think it's a good opportunity to discuss a detailed balance. So when we look at the transition rate between state, so there is a state k and the state k prime, and there is a transition rate between state k and k prime. And the transition rate between these two states is wk to k prime f of k times 1 minus f of k prime. So this is roughly how many electrons go from the state k into the state k prime per unit time. And it has an obvious probabilistic interpretation. To go from state k to state k prime, you need to have state k occupied, state k prime empty, and wk prime is the probability to go from one state into another. Then, so this is the flux. So this is the flux from k to k prime. Then you can ask, what is the flux from k prime to k? And obviously, flux from k prime to k looks very similar. So this is the flux from the state k prime to state k. And now, imagine for a second that the system is at equilibrium. What does it mean? And what it may mean, it's not necessarily true, but it may happen that the equilibrium. So okay, let me divide the statement into two. The first part is accurate. So if you're at equilibrium, what it means that the number of electrons at the state k does not change, and neither does the number of electrons at the state k prime. So this is what we know for sure. If you're at equilibrium, then the occupation of any state does not change in time. In particular, what might happen, and this is what usually happens, that there is a pairwise balance between any pair of states. So if you look at the pair state of k and k prime, that the number of electrons that pass from state k to k prime exactly cancel the number of electrons that go from state k prime to k. This is not a law of physics, but this is what happens in the vast majority of simple models. So unless you think about some very sophisticated situation, normally you will not only be at equilibrium, but you will have an equilibrium that satisfies pairwise equilibrium. The flux between any pair of states equilibrate. And this is called detailed balance, not just a balance of electrons at any state, but there's also a balance of fluxes between any two states. This is typical situation for many collision processes. So let's assume, this is an assumption, let's assume that there is a detailed balance. And by the way, of course, detailed balance does not necessarily is not limited to electron phonon scattering. Detailed balance can also exist in electron disorder scattering and electron scattering, and you name it, all scatterings in the world may or may not satisfy detailed balance, and usually they do. Okay, so let us now look at this expression for detailed balance and what it means. If I compare these two terms, I can divide this equation by 1 minus fk. So then I'm getting w k prime to k f of k prime is equal to fk 1 minus f of k prime divided by 1 minus fk w k to k prime. And then I look back at my collision integral. I go back in my collision and look at my collision integral. My collision integral reads sum over k prime w k to k prime 1 minus f of k prime using detailed balance 1 plus fk 1 minus fk, and this is equal to sum over k prime wk to k prime 1 minus f of k prime divided by 1 minus fk. Nothing dramatic has happened here. I just assume that my model is sufficiently simple so it satisfies a detailed balance, and this allowed me to represent the scattering term in a more concise form. Okay, now let's compute the absorption and emission scattering times using this formula, and we already know how it works. So these two processes are essentially the same. One comes with a number of phonons, another comes with a number of phonons plus 1, because absorption requires a pre-existence of the phonons in the material, and emission does not. You can emit phonon even at 0 temperature. So n and n plus factors that are absolutely standard. You already know this by now. So 1 over tau k absorption, this one that requires a pre-existent phonon. So the integral will be 2 pi over h. So let me denote by dk in the power d an object which is d-dimensional k over 2 pi in the power t, just not to write. So in particular, d is 3k over 2 pi 3 for d equals 3. So this will be a notation that will simplify integrals. So this is d k prime, and all the factors of 2 pi are inside. dq, these are d-dimensional integrals. B of q delta k prime minus k minus q. So this is a momentum conservation of electron phonon scattering. Then there's an energy conservation of electron phonon scattering process. It's absorption, so we need to have a pre-existent phonon. And then the factor that I just derived for the local balance condition. Okay, now integrating over k prime and eliminating one delta function, we get integral dq. Well, this is three-dimensional integral. B of q, energy conservation, plus omega q. And here, n of omega q. And here 1 minus f epsilon k plus omega q. 1 minus f of epsilon k. Okay. Just brute force calculation, so you can't help it. So we have energy conservation. Let's look into it. So epsilon k minus epsilon k plus q plus omega q. So these guys are vectors. So this is in the model of effective mass. This is this guy minus k plus q square over 2m plus s absolute value of q. This is equal to minus k times q over m plus q square over 2m plus sq. This is approximately, now remember, temperature is much smaller than epsilon Fermi. So typical momentum will be of the order of k Fermi. Therefore, k over m absolute value is essentially V Fermi. So this is minus V Fermi cosine theta times q plus q square over 2m plus sq. Therefore, the delta function here, so this delta function of the expression there is essentially the delta function of, is essentially 1 over q V Fermi delta function of cosinus theta plus q over 2k Fermi minus s over V Fermi. Sorry, here I made a mistake. It's minus q squared.
Dima? In the last equation inside the delta function, S is divided by what?
By V Fermi.
Ah, okay.
Yeah, but now we see that if q over 2k Fermi is larger than our S over Fermi, and remember that this is always very small. So if this condition is satisfied, if q over 2k Fermi happens to be larger than this, in other words, q larger than 2k Fermi S over V Fermi, and this is electron mass times sound velocity. So given this condition, we can simplify delta function and say that energy conservation delta function is replaced by 1 over q V Fermi delta function of cosine theta plus q over 2k Fermi. We should check that this assumption is satisfied. But if it is, then okay, then we assume that that's correct. We go to polar coordinates. So we are saying once again, integral over d3q will be replaced by 2 pi over 2 pi cube, integral from 0 to k d by q square dq, integral minus 1 to 1 dx. And this is essentially 1 over 2 pi square integral from 0 to k d by q square dq, integral from 0 to 1 dx. So it means that the integral d3q delta function of epsilon k minus epsilon function k plus q plus omega q turns out to be 1 over 2 pi square 1 over v Fermi, integral from 0 to k d by q square dq, 1 over q, integral from minus 1 to 1 dx, delta function x plus q over 2k Fermi. This is equal to 1 over 2 pi square v Fermi, integral from 0 to k d by q dq, and therefore 1 over tau absorption will be equal to 2 pi over h, 1 over 2 pi square v Fermi, integral from 0 to k d by q dq, b of q, n of omega q, 1 minus f epsilon plus omega q, 1 minus f of epsilon k. Similarly, 1 over tau emission k will be 2 pi over h, 1 over 2 pi square v Fermi, integral from 0 to k d by dq times q times b of q. Here will be 1 plus n omega q. And here will be 1, and here everything else will be the same. Sorry, almost. Absorption and emission. So here, omega is added to the energy. Here, omega is subtracted from the energy. And 1 over tau k is a 1 over tau k absorption plus 1 over tau k emission. Okay, so there are two processes. One process is absorption. So you have an electron at the state k. It absorbs phonon with frequency omega q and goes up in energy. So its energy becomes epsilon k plus omega q. And this is this guy. And another process is called emission, and this absorption. So it requires pre-existent phonon because you gain energy from phonons. So you need to have phonons to gain energy. Therefore, this is proportional to n of omega q. And another process, you have an electron at the state k. You emit, electron emits phonon at frequency omega q. It goes down in energy. So its energy is now epsilon k minus omega q. This process does not require pre-existent phonon in the system. Therefore, it comes with 1 plus n omega q. And it loses its energy. That's why here it's epsilon k minus omega. So all them together are combined into 1 over tau k, which is sum over 1 over tau k absorption plus 1 over tau k emission. And I can write it as 1 over 2 pi v Fermi, integral from 0 to k d by dq times q times b of q. And here will be n of omega q, 1 minus f epsilon plus omega q, 1 minus f epsilon plus 1 plus n omega q, 1 minus f epsilon minus omega q, 1 minus f epsilon. Okay, so let's denote the whole bracket. Let's give it some name. So let's call the whole thing phi plus. We will use it later. Now consider the limits. So let's complicated expression. I cannot compute it for all cases, but I can compute the limits. For if temperature is much larger than omega t pi, then we know that number of phonons is large, and it can be estimated as temperature over omega t pi. Then I'm replacing n by temperature of omega t pi, and 1 over tau k is equal 1 over 2 pi v Fermi, integral from 0 to k d by dq times q times b of q. Yeah, and in this case, there's no reason. So n of omega is approximately equal to n of omega plus 1. So it makes things easier. T over omega d by, and here will be 2 minus f epsilon plus omega minus f epsilon minus omega, 1 minus f of epsilon. Okay, so when temperature is much larger than omega d by, then, okay, so my picture is as follows. So there are energy, there's epsilon Fermi. We decided that temperature is much smaller than epsilon Fermi. Therefore, there'll be a window of the size of temperature of energies that are contributing to the scattering time. However, we already decided that temperature is much larger than omega d by. Therefore, typical energy counted from the Fermi surface will be of the order of temperature. This window is of the order of temperature, which means that it will be much larger than omega d by, which means that here I can neglect the difference and I can replace 2 minus f epsilon plus omega minus f of epsilon minus omega. I can forget about this difference and say that this is 2 minus f of epsilon, 2 minus 2 f of epsilon. And therefore it's 2 times 1 minus f of epsilon. And therefore the whole term is essentially 2. Therefore I continue And I'm getting that this is 2 divided by 2 pi v Fermi, integral from 0 to k d by dq times q times b of q times temperature of omega d by. And you have seen this type of calculation before. So I'm getting again temperature over V Fermi k d by. So what has changed? What has changed in comparison to the Boltzmann gas? So I remind you, if you, so this is 1 over tau k in the Fermi gas, but much larger than omega d by. And if we recall what we have studied before, in the Boltzmann gas, then we had the following formula. And this was for temperature larger than everything. So the difference is that, so this was the Boltzmann gas. This is a Fermi gas. So the difference is the replacement of m over k by V Fermi. So essentially we're saying that we move towards a Fermi gas limit. Typical k will be k Fermi, and therefore this prefactor will be 1 over V Fermi. Nothing too dramatic. Okay, now let's continue. Let us now discuss low temperatures. Meaning temperature is much smaller than omega d by. So what happens there? So let's go back. Let us look at the object we called phi plus. And it has two terms. Term that comes with a n plus 1, and terms that comes with n. Let us give them, no, let's call this guy psi plus, and this called psi minus. So assume that now, so temperatures is the smallest energy scale. So there is a well-defined Fermi surface, which is absolutely filled. Let us consider an electron which is electron above Fermi surface. Let's consider an electron above Fermi surface. So let's assume that energy is positive. So what can we say about low temperature limit of this expression? What survives in this expression when temperature goes to 0? Let us decide that we are looking at the scattering rate of electron that is above Fermi surface. We can think about it as follows. The system is at equilibrium. We added one electron and placed it above Fermi surface. And we want to compute the time it takes for this electron to lose its, to equilibrate its, to scatter essentially. Yeah? So this is the purple object is the object that controls the scattering rate. So what survives in this object when temperature goes to 0?
The second term, the psi plus?
Correct. Just a second, it disappeared. It's correct. So the first term now drops because there are no phonons. In the second term, this thing also drops, but one survives. Moreover, we decided that epsilon is positive and bigger than temperature. Let's look at epsilon positive and bigger than temperature. It means that n of omega is 0 and f of epsilon is 0. So we are left with this expression. Essentially, I can say that where do I write it? This phi plus this. So essentially, I'm saying that this phi plus is approximately 1 minus f epsilon minus omega. That's the only thing that survived. Everything else drops down in this limit. Now I need to decide where do I place epsilon. You remember there was a considerable simplification of the delta function, of the energy conservation delta function that required that just a second. No, sorry, just, okay, let's go slowly. It will come automatically. I'm not sure, was it, I'm there yet or not. So there is the integral, right now, integral over 1 over tau k becomes 1 over 2 pi v Fermi, integral from 0 to k d by dq times q b of q 1 minus f of epsilon minus omega q. So it means it means that for now I need to resolve the constraint. I need to say what are the, so the only contribution to this integral requires that epsilon, so this means that there's a condition epsilon minus omega q needs to be positive, otherwise this integral is 0. So it means that epsilon needs to be larger than omega q. That's the condition. That's the limit of the integration over q, where this thing is not 0. Okay. Now, if now the maximal omega q is of course smaller than omega d by. Therefore, if epsilon is larger than omega d by, then this guy is identically 0, and the brackets are identically 1. And therefore, if energy is larger than omega d by, we are left with 1 over tau k being equal to 1 over tau 2 pi v Fermi, integral from 0 to k d by dq times q times b of q. We have seen this integral before. It's almost the same integral. So it's 1 over 2 pi v Fermi b0 integral from 0 to k d by dq times q square. It's equal to b0 k d by cube over 6 pi v Fermi. And this is, in terms of our old friend, nominal scattering time, is this time times s over v Fermi. So we see that the time that we got now is parametrically, so the scattering rate that we got now is parametrically smaller than the scattering rate in the case of large temperatures. So it means Pauli blocking suppresses the scattering, lepton-Bonan scattering. So if before it was roughly the nominal scattering time, that now it's parametric, the rate is parametrically smaller, the scattering time is parametrically longer. Okay, so we got something, that's the statement number 1. Statement number 2, that this thing is k independent. Or energy independent. And essentially, it's even temperature independent. So it does not depend in this range of parameters. It is this scattering time is completely built of some material parameters. Okay, but that happened if we assume that energy is larger than omega d pi. So this was in the range of parameters. Temperature is, sorry, energy was much larger than omega d pi. Now, if energy is smaller than omega d pi, which is equal to sk d pi, then the condition epsilon minus omega q greater than 0 assumes that energy is larger than sq, and this restricts integral over q. So integral over q now runs between 0 and epsilon over s. So we now need to go back and essentially replace this integral, and it's no longer equal, it no longer goes up to kd pi, rather it now goes up to energy over s. Okay, let me write it accurately. So 1 over tau k in this regime is equal to 1 over 2 pi v Fermi, integral from 0 to e over s dq bq times q. This is b0 over 2 pi v Fermi, integral from 0 to e over s dq q square, and this is equal to b0 over 2 pi v Fermi q cube over 3 from 0 to e over s, and this will be equal to 2/3 over 1 over tau Fermi nominal epsilon to kd by s cube. So this is again material constant, but now we got a function that explicitly depends on the energy. So we got the result that scales as energy in the power cube. So let us try to summarize this story. So what happens when temperature is much smaller than omega t pi and temperature is much smaller than epsilon Fermi? We know that phonons have a momentum that can be as maximal as thermal, Therefore, the value of the momentum temperature over S in the lower temperature region will be much smaller than the Fermi momentum. Okay, so it means that if you have an electron somewhere close to Fermi surface and it scatters this Fermi momentum, there are two things that we need to remember. We need to remember energy conservation and momentum conservation. Energy conservation tells us that Q times S is equal to the change of electronic energy, which is equal to V Fermi times Q. And now V Fermi is much greater than S. So there is a electron somewhere in the state K. There is a Fermi velocity, which is essentially close to Fermi. It's K Fermi over N. And there is this product, V times Q, and it needs to be equal to the product Q times S. So what does it tell us? How can it scatter? If it started at the momentum K and it goes to some other momentum K prime. So the size of this sphere is K Fermi, and it's much larger than the change of the momentum acquired by scattering. So this already tells us that the scattering is very limited. We cannot go far from this point. We only limited by some very small radius of scattering, which is T over S. But there is more to it. If we look at this expression, we see that the product of V times Q needs to be small. So it means that V must be almost perpendicular to Q, or Q must be almost perpendicular to V. So it means that electron scatters. Can you tell me what it means? How does it scatter? What should I do symbolically or approximately to understand how will it scatter? What the conservation law will tell us?
Maybe expanding it? I'm thinking it might do circles or something, because the energy needs to remain constant and V times Q is small.
So this is this equation. This is energy conservation. This is energy conservation.
Yes. No, so I'm saying if V dot Q is small, then that means that they're perpendicular to each other.
So it means that the scattering is perpendicular. It means that the scattering is perpendicular to K.
Yeah, so it moves in, like, I mean, it looks like a circular motion.
It moves parallel to Fermi surface. It means that it scatters, it does not change its magnitude. Instead, it performs a perpendicular scattering. Yeah. So it goes from the state K to the state K prime with angle theta between these two. And the scattering and the change of the momentum is practically perpendicular to the momentum. And the size of this angle is Q thermal over K Fermi. So it's temperature over S and K Fermi. So it's this is the change, this is the picture. So in the process of a single scattering, there is a change of electronic momentum parallel to Fermi surface at low temperatures. The magnitude is this, so this is the and the resulting scattering time will be some nominal scattering time, which is just a constant, times energy counted from the Fermi surface in the power 3. And you can go back to the equation and understand why it's a power 3. So what is this time that we have computed? What is the physical meaning of this time? What happens after this time? Or what this time quantifies?
After this time, the electron should be in equilibrium with the rest of the system?
So what is the, did it lose its energy? So assume that the energy of this electron is much larger than temperature, and this is what we indeed assumed. Yeah? Did it equilibrate itself? Did it lose the energy? Did it lose the energy? Did it completely lose its energy? Was the energy change in this process of the order of energy?
Can you repeat that? I had connection issues.
So how do we know it equilibrated itself? It would equilibrate itself if two things would happen. If its momentum got equilibrated and its energy got equilibrated. So things would be equilibrated if the change of the momentum would be of the order of momentum, and the change of energy would be order of the energy. If these two conditions are satisfied, then the electron equilibrated itself with the entire system. Did it equilibrate its energy and momentum, or momentum?
No, I think the energy didn't change and the momenta only changes slightly.
Correct. The momentum changed by a tiny bit. And I don't remember the change of energy off the top of my head, but I think you are right. I don't want to start computing it right now, but my impression but it did not equilibrate either. But probably I should it's a nice exercise to go back and compute how much the energy changed, but definitely the momentum did not equilibrate. So what this time scale means is it means that there was a single collision. That's it. There was a single collision between electron and phonon. In the process of this collision, the momentum changed by a tiny bit. And okay, I need to go back and compute what was the effective energy change, but there was some energy change, but we need to. So it was, the energy change was essentially of the order of omega q. Yeah? Energy change was of the order of omega q. So Q was, no, the energy, no, I think the energy change was of omega Q was essentially of the order of energy, huh? That was the condition for omega Q. So I think the energy has changed by the order of magnitude. So the change of energy was essentially of the order of energy. So the energy did change. The energy did change. So energy equilibration did happen, but the momentum equilibration did not. So if we assume that energy is below, if energy is bigger than omega d pi, that energy equilibration did not happen. If energy is smaller than omega d pi, then it did equilibrate. So essentially electron lost, emitted a phonon, lost, and so essentially the picture is that electron with energy epsilon emits a phonon with omega q of the order of epsilon k and loses its energy.
But retains its momentum.
But the change of the momentum is quite small.
So 1 over tau k is the time for a single collision in which it equilibrates with respect to the energy, but not with respect to momentum.
Yes. So, and then you may ask the following question. Imagine you have a clean sample. Imagine that you have a clean sample. So it means that no disorder. Yeah? Just imagine for a second, there's no static disorder. And then you are interested or in other words, what is the contribution of what is electron phonon scattering does for electric resistivity. If you remember, electric resistivity has everything to do with the relaxation of the momentum. You created a current, you pushed a current by external force, and then disorder counterbalance this force by randomizing a momentum. It didn't care about energy relaxation. So then you can ask, what would be the contribution of the electron phonon scattering to electric resistivity? We see there is an electron phonon scattering time that scales with energy in the power cube. But what can we tell about transport time? We see that these two things seem to be parametrically different in this case, because scatterings do happen much more frequent than the change, but at the time it will take to randomize the momentum. You see my point?
I think so. I'm not entirely sure.
Okay, so I think it's a good time for us to stop, because I think I posed the question. And hopefully next time we will try to understand, to answer this question, to understand it, and then to see how naturally electron phonon scattering give rise to the variety of regimes of different temperature behavior. Now these things, first of all, they're fundamentally important, but also in all these modern materials, when people observe some resistivity as a function of temperature, they like to say that this is Fermi liquid behavior and this is non-Fermi liquid behavior, because you expect temperature in this universal power, and now you expect temperature in other power. Now, as you will see, just a simple electron phonon model will give rise to a number of regimes with different temperature behavior for different conservation laws, for different temperatures. So essentially we'll see that there are different dominating scattering mechanisms, different typical change of the momentum, and we will get resistivity as a function of temperature that scales differently with temperature, purely due to electron phonon interactions in the very simple model. Now, of course, you can enrich this model, allow for other type of scattering processes, other type of bosonic modes, and generate as many universal regimes of resistivity, of electric resistivity as a function of temperature. And I'm not saying that there's no non-Fermi liquid behavior. I'm just saying that you need to be extremely cautious with that, because even simple scattering processes may give rise to different resistivities, and you need to be very careful distinguishing between just scattering time and transport times that enter into the particular quantity that you measure. So if you measure electric resistivity, it's controlled by momentum relaxation time, and momentum relaxation time can be parametrically different from just lifetime. And you see it already on the level of very simple models. Now, and people measure different, of course, different responses, different time scales enter into these responses, and all these time scales may and usually scale differently with temperature, generating the whole zoo of regimes, especially for anisotropic spectrum. And therefore you cannot make an oversimplifying statement what you expect or do not expect for say Fermi liquid. Okay, I hope that next time we will finalize the discussion of electron phonon scattering in simple models. So do you have any questions?
No, I think I just need a bit of time to process.
Okay, good. People who did not submit homeworks, please do. I will publish a new home assignment soon, hopefully in the next couple of days. So if no more questions, then goodbye, everyone.